All right, today we're doing an example about wave propagation in lossy media. This is example 7-3 in the book. We're given a sinusoidal electric intensity, so that would be the electric field E, with amplitude 250 volts per meter, frequency 1 gigahertz, in a lossy dielectric with epsilon r equals 2.5, the relative permittivity, and the loss tangent of 0.001. And we're supposed to find the dissipated power per meter cubed. And this is not required by the problem, but let's also plot the magnitude of the electric field versus distance, just so that we can see what happens to the amplitude as that power dissipates. So to find the dissipated power, we're going to need sigma, but we're not actually given sigma, so we have to find it. We are given the loss tangent. So let's use the relationship between the loss tangent and the material parameters. So loss tangent is equal to epsilon double prime over epsilon prime, which is, unless we have a complex epsilon for other reasons, that's going to be sigma over omega epsilon, which is sigma over omega epsilon naught epsilon r for us, which is, here's our mystery sigma divided by 2 pi 10 to the 9th times 10 to the minus 9th over 36 pi, which is approximately equal to epsilon naught times 2.5. Wow, there's not a lot of room in there. All right. If you work that out, you get that sigma is equal to 1.93 times 10 to the minus 4th, and that's in Siemens per meter. Then how do we find the average power dissipated per unit volume? If you remember from previously, power dissipated in a volume is equal to the integral over that volume of 1/2 the current density times the dot product with the electric field. In this case, that is going to be constant, so we can just multiply by the total volume. So we have 1 meter cubed times 1/2, J being sigma E, that becomes sigma times 250 volts per meter squared. If we work that out, the power dissipated in a cubic meter is equal to 1/2 times 1.39 times 10 to the minus 4th times 250 squared times 1 meter cubed, which doesn't actually give us any change in the actual quantity. And at the end, we get 4.34 watts per meter cubed. Well, we're going to get rid of the meter cubed because that would, yeah, okay. 4.34 watts per meter cubed. All right. That was a pretty quick problem, but it gives us a little bit less physical insight that I want. So I also want to know, how does the magnitude of that electric field depend on distance? So to do that, we have to look at the attenuation constant. In a good dielectric, the attenuation constant alpha is approximately equal to omega epsilon double prime over 2 square root of mu over epsilon prime. Here, epsilon double prime is equal to sigma over omega, and epsilon prime is equal to epsilon. we define alpha in terms of epsilon double prime and in terms of epsilon prime because sometimes, especially at higher frequencies, loss is not due to conduction. It's due to the sort of time delay and the power that's lost in polarizing and unpolarizing the little particles in your material. So then it's more correct to account for it in terms of a complex epsilon. You still get loss, but it's not really a conduction current, so conductivity is the wrong material parameter to use for that. In any case, in our situation, this alpha expression turns into sigma over 2 square root mu over epsilon, or that would be epsilon naught epsilon r. If we work that out, alpha is equal to 1.39 times 10 to the minus 4th over 2. If you remember, square root of mu naught over epsilon naught is 377 ohms, the intrinsic impedance of free space. So we can just write that as 377 divided by square root of 2.5, which is equal to 0.0166. And that is in, you can express this as Neppers per meter or as just 1 over meters. The expression for our electric field then is going to be some unit vector times 250, which is our amplitude, times e to the minus alpha z, our decay versus distance, times e to the minus j beta z, our phase term. And then if we take the magnitude of that, the magnitude of the electric field is just going to be 250 e to the minus alpha z. So let's take a look at how that varies as we move through space. I'm going to draw us a graph here. This is going to be magnitude of E on the y-axis. I'm going to start with 250 up here and kind of divide this into, I'll try and get 5 evenly spaced things. There we go. So we got 50, 100, 150, 200, 250, like that. And then we're going to look at a few different points. So that's going to be 10 meters, 20 meters, 30 meters. Those are not evenly spaced, but it's a sketch, so you're going to have to forgive me. Now, if you put this into your calculator or whatever, what you're going to have to do is you're going to have to do electric field magnitude as a function of z is going to be equal to 250 times e to the minus alpha z. And then the numbers that we're going to get here are going to be at 30, we're going to get 151 volts per meter. At 20, we're going to get 179 volts per meter, approximately. And at 10, we're going to get about 212 volts per meter. So let's put those on the plot. We start off at 250. At 10 meters, we are maybe, let's see, a quarter of the way between 200 and 250. So we're kind of like there. At 20 meters, we're at 179, so we're maybe halfway between 150 and 200. So we are right about there. And at 30 meters, we're at 151, so let's say we're right about 150. We're right about there. And then in the end, our graph looks like this. This is a very, very slow decline, but it is actually an exponential curve. It just looks straight because the variation is so slow with distance. So this is good because we were calculating the power dissipated per unit volume, kind of assuming that the electric field amplitude was constant within that 1 meter cube. And if you look at this, that's sort of like this area right up here, in which case, yeah, I think it's pretty reasonable to assume that the electric field amplitude is 250 everywhere in the cube, and that's fine. So there you go. We looked at plane wave propagation in lossy media and how power is dissipated in the medium, and then how the amplitude varies over distance.